Alright, ladies and gentlemen, welcome to the third and final video for Chapter 3, Section 1 in your Algebra 2 book, covering algebraic methods for solving systems of equations. This third and final method is known as the elimination method, and we generally only use this method when both equations are in standard form. So the idea will be that one of the things we are allowed to do with equations is add them together. So when we add two equations together, if our numbers are right, one of those variables could drop out. So what we're going to do is we are going to multiply one or both of the equations by a number. Now that's everything in that equation by a number, so that the coefficients of one of the variables are opposites, such as negative 4x and positive 4x. If we were to add those terms together, that would be 0 and x would drop out. We add the two equations together, which causes one of the variables to drop out and creates a one-step equation. We solve that equation to get one variable and substitute it back into one of the original equations to find the other. So let's take a look at example A. If you look closely here, you'll see that this is already ready for elimination. We've already got positive 2x and negative 2x in the equation. So if we added these two equations together, immediately the x cancels and we are left with negative 3y equals positive 6. We divide each side by negative 3 and we get that y equals negative 2. The elimination method is the one that you really need to be comfortable with because it's the one that you're going to use the most often. Now if y equals negative 2, we take that and we plug it back into one of the original equations. It does not matter at all which original equation, so I'll just use the first one. 2x minus 9 times y, which is negative 2, equals 34. So 2x plus 18 equals 34. Subtract 18 from each side would give us 2x equals 16, and divide by 2, we get x equals 8. Okay, so we just solve that equation, plug it back in, we solve the other equation, and we have our point. Our answer is the point 8, negative 2. Again, we list our answers to these systems as a coordinate point x, comma, y. Okay, our second example is a little bit more difficult. You'll notice that it is not already ready for elimination, so we just have to make a decision. We have to decide whether we want to eliminate x or y. The good news is it doesn't matter. You can choose to eliminate either variable and you'll get the same answer either way. So if it's me, I look at this problem and, well, I notice something right away, but you probably don't as a student. So you say, oh, well, I need to multiply the first equation by negative 3 because that would give me negative 15x. So that's what we do. We multiply the entire first equation by negative 3. That would give us negative 15x minus 9y equals negative 156. The second equation we did not touch, so it's still exactly the same. Now by now you should have noticed what I noticed right away as an experienced math teacher, and that is that when I add these two equations together, not only does x cancel, but so does y. That means I'm now looking at 0 equals negative 102. This is one of our special case situations. If you are solving a system of equations and both variables disappear on you, you look at what's left and you ask yourself, is this statement true or false? Well, 0 is clearly not equal to 102. This is a false statement. If the answer is false, then we have no solution, okay, or the empty set symbol. Okay? If it were true, there would be infinitely many solutions. Okay, so just keep that in mind. All right, on to the next example. Again, you'll notice it is not set up for elimination yet, so we simply need to make a decision. I'm going to multiply the first equation by negative 7, which will allow me to eliminate the x because it will give me negative 7x and positive 7x. So when I multiply it by negative 7, my new system is negative 7x minus 7y equals 93 times negative 7, or negative 651. I did not touch the second equation, so I'm just rewriting the second equation underneath the new first equation. And if you notice, when I add those together, x cancels, leaving me with 2y equals 733 minus 651, which is 82. That is a one-step equation where I need to divide both sides by 2 to give me that y equals 41. So if y equals 41, I'm going to plug that back into the original first equation to give me x plus 41 equals 93. And then I'm going to subtract 41 from each side, which would give me x equals 52. Again, we want to write our answer as a coordinate point, x, comma, y. Okay, last slide here. We've got 2 examples left. We have how many solutions does the given system of equations have? Well, the only way we would know is to try to set it up for elimination. So I look at this and I see that if I want y to cancel, I need to multiply the first equation by 12. So I'm going to multiply the first equation by 12. When I do that, I get 60x minus 12y equals 108. The second equation is negative 60x plus 12y equals negative 108. When I add those equations together, well, I get 0 equals 0. So I ask myself, is that true or is that false? That is a true statement, which means there are infinitely many solutions. Okay? So my answer over here would be infinitely many. Example 4 is a real-world problem. Real-world problems tend to be relatively straightforward in the way they're written. It says at a concession stand of a football game, Molly buys 3 drinks and 2 candy bars for $7. Eric buys 2 drinks and 4 candy bars for $8. So we're going to let x be the cost of a drink, and we're going to let y be the cost of a candy bar. It's important that we know what our variables stand for. So if you choose to use D for drink and C for candy bar, that's fine too. But you need to know what your variables mean. Now this says Molly buys 3 drinks and 2 candy bars for $7. So equation 3x plus 2y equals 7 represents Molly's order. Eric buys 2 drinks and 4 candy bars for $8. So that equation, 2x plus 4y equals 8, would represent Eric's order. Now we could solve this entire system, or we could only find the value of a drink, which would allow us, we need to find x, right? So let's eliminate y. To eliminate y, we need to multiply the first equation by -2 so that this becomes a -4, and it'll cancel. So when we do that, our system becomes -6x minus 4y equals -14, and 2x plus 4y equals 8. We add those equations together, y cancels, and we're left with -4x equals -6. We divide both sides by -4, and you're going, but Mr. Wills, that doesn't divide evenly. You're absolutely right. But this is a problem where a decimal would be appropriate because it's a cost. So dollars and cents is not an unacceptable answer. Now, if we needed to know the value of a candy bar, we could keep going by simply plugging x into the equation to solve for y. But we have what we need here. It asks how much does 1 drink cost? That's saying what is x? We just found that. A drink costs $1.50. Thank you very much, ladies and gentlemen, for your time and attention.